Okay, so in the second part of rational functions, we're going to be looking at rational functions that are not of that form where we can see the transformations. So sometimes we have a rational function, we're like, oh, okay, that's just that reciprocal function, shifted left 2, down 5, stretched vertically by a factor of 3, and we can see that. But what do we do when it's not written in that form? What do we do when it's written in, look at these examples right down here, g of x, h of x, k of x. These are still rational functions. So we're going to do a little bit of discovery to help us be able to graph these. So first of all, horizontal asymptotes. Remember that horizontal asymptotes are formed as x approaches positive infinity and negative infinity. They're all about the end behavior. So what you're asking yourself is there some number the function converges to as the absolute value of x gets really big? If there is, then it creates a horizontal asymptote. So let's look at each of these. Okay, so starting with the first one, I've got it graphed here. And again, we're not looking in the interior. We're looking as x gets really big. So as it goes to negative infinity or goes to positive infinity. So I've also created a table right here. So I'm just going to kind of come down and start typing in some big numbers. I'm going to type in 10, 100, 1,000, 10,000. And you can see that as I type in those numbers, what does it look like those y values are getting closer and closer to? You can also drag your graph this way. And as we drag our graph this way, we can see that it seems to be getting closer and closer to 0. And we can do the same thing for the left side. Let me drag this back real quick. So we notice as we go towards negative infinity, and we look at bigger negative values of x, that our y values are also getting closer and closer to 0. The only difference is that they're getting closer and closer to 0 from the negative side. So we can clearly see that this one would have a horizontal asymptote at y equals 0. Here's the second graph. This one's really funky looking because it actually doesn't have a vertical asymptote, and we're so used to rational functions always having vertical asymptotes, but they don't necessarily have to. If you were to take the denominator of this function, 5x to the fourth plus 1, and set it equal to 0, and find its zeros, it only has imaginary roots. So therefore, there's no real number that makes the denominator equal to 0. Therefore, it doesn't have a vertical asymptote, but it's still a rational function. And again, if we look as x gets really big in the negative direction and in the positive direction, this function converges towards 0. So let's look at the last one. Last one's kind of funky looking too, but same thing. We notice that as x gets really big, that the y values are closing in and getting closer and closer to 0. And sometimes we can look, that's why I'm using Desmos, it's a little easier to see it. But we can also do it by creating a table and looking at those values. And all I do is just kind of make some bigger values in here. And you can do this with your graphing calculator also. And type in big numbers and see what's happening. The bigger you make those x values, we can see that those y values just keep getting closer and closer and closer to 0. So pretty much the conjecture here is anytime the degree of the denominator is greater than the degree of the numerator, we will always have a horizontal asymptote at y equals 0. Of course, you can just memorize that, but when you get to calculus next year, you're going to have to look it back up. It's much more important to understand why that happens. If you understand why that happens, you'll never forget it. You don't have to sit there and memorize these rules. The reason why that happens is because as x gets really big, the higher the power of the function, the higher the degree is, the faster that function's growing. A quadratic function grows faster than a linear function. A quintic function grows faster than a quadratic function. So as x gets really, really big, the denominator is so much bigger than the numerator that it starts to get closer and closer to 0. A small number divided by a big number is going to converge to 0. Another way to look at it is, as x gets really big, this part of it's not going to matter. So literally, you're looking at these leading terms. You've got 2x divided by x squared, and if I was to reduce that, that would be 2 over x. So as x goes to infinity, 2 over x goes to 0. Think about it. 2 out of 10, 2 out of 100, 2 out of 1,000, 2 out of 1,000,000. The thing is, it never actually gets to 0 because of the other little stuff that I scratched out, and because they don't completely like reduce up. They get closer and closer to. Think about what we know about exponential functions and those types of things. All right, so I would like for you to look at the next three, and whether you're using your graphing calculator or Desmos, I'd like for you to graph each one and see if you can figure out what is the horizontal asymptote and write it down. And so pause the video, do that, and then we'll talk about it. Well, looking at this first one, it does not look like it's converging to 0 this time. So we can graph it and we can drag, or in your graphing calculator, you can change your window around. Gosh, it looks like it seems to be getting closer and closer to 6 units if I count those units up. But a better way is probably to look at a table and look at really big values of x. And what we see from our knowledge of converging is those numbers seem to be getting closer and closer to 6. For that second one, it looks like if you drag your graph around as you look as x gets really big, that it seems to be getting closer and closer to 1. One thing I want to show you, especially if you're using Desmos, if I was to come down here and I was to type 10,000, it actually tells me it's at 1. It's not. It's just that it's so close to 1 that it just finally starts rounding it. If you use your graphing calculator, it'll do that, but if you actually click on the y value in the table, it won't be 1. It'll show you, the actual value. This third one, I want to show you how you can do the same thing that we did in Desmos in your table. What you can do is when you come up here to your table setup, let's say you want to start your table at 1. Instead of having it in auto for the independent variable, put it over to ask. And then when you go to your table here, it doesn't have any x values, and you can type in what you want. So you can type in 1 and then type in 10 and then 100. And then 1,000, and I'm just picking these because they're easy. I can type in 10,000 and so on and so on. And again, you can see it looks like it's getting closer and closer to 3/4. This actually ended up rounding, but if you go up a little bit, normally it doesn't, but I guess it just got so close to it, it couldn't help it. But you can see it actually doesn't get to 0.75. It is converging towards there. Just if you do this, make sure when you're done that you go back to your table setup and you take it back out of ask, because then I know what happens. You get there and you're like, where did my table go? So make sure you keep it in auto. Okay, so for all three of these functions, the degree was the same. So if the degree is the same, if both the numerator and the denominator are linear, or they're both quadratic, the only thing that would make it one grow faster than the other is their leading coefficient. Again, as x gets really big, the leading terms are what controls this. So that +1 - 1 doesn't really matter. So what you have is 6x divided by x, which is just going to leave you with 6. Same thing here. 2x squared divided by 2x squared. The x squared is reduced, so 2 divided by 2 is 1. Same thing here. Those x cubes are going to reduce, so you're left with 3/4. And again, it never actually gets there because of the stuff I scratched out. But it gets so close to it that it's converging towards it. And that's why anytime the degree of the numerator is the same as the degree of the denominator, the horizontal asymptote will always be the leading coefficient of the numerator divided by the leading coefficient of the denominator. All right, so the third situation, what if the numerator degree is higher than the denominator degree? If that happens, there is no horizontal asymptote. For example, if we had the function x squared plus 1 divided by x minus 1. As x gets really, really, really big, if you kind of just ignore this part, we are left with x squared over x. And if you divide x squared by x, you're still left with y equals x. So as x goes to infinity, so does the function go towards infinity. So it doesn't have a horizontal asymptote because it never converges. Maybe pause the video, get down what you need, and then let's go to the next page. So for each of these functions, I would like for you to state the horizontal asymptote and the vertical asymptote. Remember, vertical asymptotes are where the function's undefined. So to find those, we set the denominator equal to 0 and find what values will make the denominator equal to 0. Pause the video. When you're finished, start the video back. So for the first one, the degree of the denominator dominates. It is larger, so therefore we have a horizontal asymptote at y equals 0. When we factor that x squared minus 4, we get that the vertical asymptotes would be at x equals -2 and x equals 2. Make sure when you write your asymptotes, you write y equals or x equals. Don't just write a number because that makes no sense. They're actually lines, imaginary lines on our graph. So if you tell me the vertical asymptote's at -2 and 2, you're not going to get any credit for that. That doesn't make sense. The second one for h of x, it does not have a horizontal asymptote because the numerator degree is dominating. Therefore, this function goes off to infinity or negative infinity. Vertical is at x equals negative 2/5. And the last one, they are both linear expressions, so therefore, when we do the leading coefficient of the numerator divided by the leading coefficient of the denominator, our horizontal asymptote is at y equals 3/2. Set the denominator equal to 0. Our vertical asymptote is at x equals negative 1/2. And we should be able to do this without technology. We use the technology on the first page to help us discover why we have horizontal asymptotes. All right, so how are we going to graph these rational functions that are not in one of those transformation forms from the reciprocal function? What we're going to do is, if possible, we're going to factor the numerator and denominator. And then we're going to find the intercepts if they exist. So get your x-intercepts, y-intercepts. We're going to find the horizontal asymptote if it exists. Find the vertical asymptotes if they exist. Once we get all those things, we're going to graph them on our graph paper, and then determine the behavior of the graph in the regions formed by the vertical asymptotes. So once you get your vertical asymptotes on there, you're going to substitute an x value within each region and figure out, am I graphing above this horizontal or below this horizontal, to get a little sketch of the graph going. So let's start with this first function. Okay, so when we start with this first one, we have x squared minus 9 in the denominator. That's that difference of squares, so we know that factors to x plus 3, x minus 3. All right, so let's start by finding our intercepts. To find our intercepts, it's pretty simple. We're going to find our x-intercept and our y-intercept if they exist. So I'm just going to come over to the side, and I'm going to put 0 in x and 0 in y. So to find our y-intercept, it's pretty simple, guys, because we know anytime we have a y-intercept, x is 0. So if you're looking at just a polynomial, you know it's the constant term. Since a rational function is a polynomial divided by a polynomial, all we have to do is take the constant term of the numerator and divide it by the constant term of the denominator, and that gives us our y-intercept. Again, you can substitute 0 in for x in the numerator and denominator, but you would be left with positive 2 over negative 9, which is negative 2/9. All right, to find our x-intercepts, we know that y is 0. So I'm just going to write this out this one time, but after that, you will be able to do this much quicker. Every time you find an x-intercept when it's in this fractional form, what happens is you substitute 0 for y. And then to solve this, you multiply each side by the denominator. Well, because one of the sides is just 0, when you multiply that side by the denominator, you ultimately just end up with 0. So anytime it's just one fraction and you are trying to find the x-intercept, technically all you have to do is set the factors in the numerator equal to 0 and solve, and those are going to be your x-intercepts. As we can see right here, our x-intercept is at negative 2. All right, so let's state our asymptotes. Our vertical asymptotes for this one are going to be at x equals negative 3 and at x equals positive 3. Our horizontal asymptote is going to be at y equals 0 because the denominator is dominating. The degree of the denominator is greater than the degree of the numerator. All right, so to graph this, I want to put on here our vertical asymptotes and our horizontal asymptotes. Once we do that, it divides our graph into 3 regions. Since we have 2 vertical asymptotes, we have 3 regions. Then all we have to do is substitute x values into the function to find a point or two. All we need to do is know, do we graph above the horizontal asymptote there or below the horizontal asymptote there? So if we go over to this left region, we would want to substitute in, I don't know, let's say negative 4. And so if you want, you can kind of just continue your x and y chart you did over here. So what if we substituted negative 4? Well, in the numerator, that would be negative 4 plus 2, so that would be negative 2. In the denominator, negative 4 squared is 16 minus 9, which would be 7. So we get negative 2/7. So what that tells me is if I'm on the most left part, when x was negative 4, y was negative 2/7, and that tells me for this part, it's going to be graphed below. And it's just a sketch. When we graph these, we use our asymptotes to guide our graph. I'm not going to be looking for 5 million points on these guys. Just get a point or two so you get an idea of what it looks like. Now this one's a little tricky because it has a middle section. And sometimes in a middle section, it'll do like what I like to call a U-E. It'll look kind of like a parabola. But sometimes it does like a twisty where it actually crosses the horizontal asymptote. Now you're like, what? But what you have to understand is horizontal asymptotes are not where the function's undefined. They're what the function converges to as x gets really, really big. So it's okay to cross a horizontal asymptote in the interior of the graph. Well, luckily, we already have some points in that region because we found the y-intercept to be at -2/9, which would be about right here. And we found the x-intercept to be at -2. And the fact that I actually have an x-intercept tells me this one's probably going to be a twisty. So I might want to get one more point. So I'm going to substitute 2 in. And again, guys, we should be able to do this without our calculator. And if I substitute 2 in, that gives me 4 in the numerator. And then 4 squared minus 9 would be -5 in the denominator. So it gives me -4/5. So that tells me when x is 2, y is -4/5, which is a little bit lower, and that's what lets me know this does a little twisty in here. If it was a U-E, it would have been either above the horizontal asymptote or below, and you would have seen the symmetry in the points. All right, so then over here for this last section, maybe we substitute in +4, and we get 6 in the numerator. And when we do that, that's 16 minus 9 in the denominator, so that comes out to be 7. So the fact that we get +6/7 tells us that when x is 4, we're up here, and it tells us that this is going to be in this top section. And then the only other thing it asks us to do is state the domain. So in this case, the domain would be all real numbers except for -3 and +3. So you can write it out like that. You can say all real numbers except -3 and +3, or you can write it in interval notation, -infinity to -3, and union with -3 to 3, and union with 3 to infinity. But I'll tell you, if you have a lot of restrictions, don't stress about writing that many intervals out. So since we did the last one, I want you to pause the video and try the next one. Go through all the steps. When you're finished, start the video back. So for this one, the numerator is not factorable with rational numbers. You actually could factor it, but you'd have those square roots in there. But the denominator is, so we can see our vertical asymptotes are at -2, and x equals -2, and x equals +2. The degree of the numerator and denominator are the same, so leading coefficient over leading coefficient, 1 divided by 1, gives us a horizontal asymptote at y equals 1. The y-intercept is at 5/4 because -5 divided by -4 is +5/4. So we can go ahead and plot that right over here on our graph. So 5/4 would be 1 1/4. So it'd be right up here above that horizontal asymptote. And then our x-intercepts are at positive and negative square root of 5. Now, since we don't have a calculator, you have to think about it. If the square root of 4 is 2, the square root of 5 is a little bit bigger than that. So obviously these x-intercepts are, right a little bit more than 2 right here and right here. And the great part is since that's on the outside of these two vertical asymptotes, I can go ahead and graph that part. I don't have to substitute any x values in because I've got it. We're good to go. But for the inside part, we have to figure out, does it do a little twisty or does it do a little U-E? So what we're going to do is substitute in some more values. So I'm going to choose -1 and +1 to see what happens. If we substitute in -1, that would give us -1 squared is 1. 1 minus 5 is -4. So I'm going to write that real quick. And then same thing, we get 1 minus 4, which is -3. And -4 divided by -3 is +4/3. And since -1 squared and +1 squared are the same thing, when we substitute in 1, we're also going to get 4/3. So 4/3 is 1 1/3. So when we plot that on there, 1 1/3 is a little bit higher than 1 1/4. And we've got that symmetry there. So that's why this one does a little U-E in here. And I'll go ahead and tell you, normally if it's like a constant divided by a quadratic, it does the U-E, or a quadratic divided by a quadratic. But if it's like a linear divided by a quadratic, normally it does a twisty. But I just always substitute some values in to make sure. Notice again, on the to find my x-intercept, I only set the numerator equal to 0 because it was just one fraction. And the last step is to state our domain. And in this case, our domain is all real numbers except for -2 and +2 because that's where the function's undefined. Okay, so tomorrow in class we will discuss the vertical asymptotes versus holes, which is the next page. We will graph some of those together and then put it all together. If you want to go ahead and look at some of the practice that you're capable of doing before we finish that, numbers 1, 2, and 3 on your practice are not where you have to figure out whether it's a vertical asymptote versus a hole in the graph, and they don't talk about any slant asymptotes. So you don't have to do that yet, but if you want to, you can. But we're spending 2 days on this lesson, so we will finish the rest together in class tomorrow.